Okay. So remember, I mean, so this is about spin representations. So recall what we did so far. So we had defined this group CLM. So this was, okay, so we discovered that this is isomorphic to full matrix algebra. Okay, so this is full matrix algebra. I mean, of course, is over C, complex numbers. And these are like huge matrices, 2 to the n times 2 to the n. So these are huge matrices, where n is this even. So this is even Clifford algebras, even complex Clifford algebra. And for the odd case, we discovered last lecture that this is isomorphic to 2 copies of this, 2 to the n c, direct sum, and 2 to the n c. Now, this endomorphism, of course, I suppose you are familiar with the notation of endomorphisms. You see, if you have a vector space like V here, right, this endomorphism of V is the set of all linear maps from V to V. I mean, with matrix multiplication, addition, scalar multiplication, this is an algebra, associative unital algebra of matrices. If you fix a basis, you get matrices. Now, the notation is that this space C to the power 2n is usually denoted by delta n, and this is called the space of spinors. I mean, so in this case, you can say, well, you already know what the space of the spinors are. It's just this vector space C to the power 2 to the n. But the point of this calling the spinors is that spin group actually acts on this space. So again, also let us recall, as we discussed, that this spin group, right, spin M, is inside this CL2n, right? We spin 2n, if you want, is inside this CL2n. So, and this Peirce isomorphism, it shows that it acts on this space. So, spin 2n, there is a map pi to endomorphisms of okay. So this is called the spinor representation. So this is called the spinor representation of the spin group. Spin 2n. So here I'm using a concept maybe you haven't seen before, so I just recall for you. the notion of representation of a group. So let me recall this notion. Again, it's just a one-liner. By representation of a group, we mean this. So what is the representation? So this group G is any group that you want. I'm not specifying anything yet. This is just a group. What is the representation of this group? Well, it's just a group homomorphism. By, so definition, if you want, a representation of G on the vector space V is a group homomorphism. I can write this group homomorphism in general as pi, for example, from G to GLV. So what is this GLV? This GLV is a group inside this algebra end of V. This is the group of one-to-one onto maps from V to V. So this is the group of invertible elements, linear maps from V to V. So this is an algebra, associative algebra. It's a vector space, but this is only a group, right? So this group is an open subset of this. V is finite dimensional, and any group homomorphism is called a representation. And in this case, because this is just a representation of this algebra, I mean, this is trivially a representation. So in this case, there is nothing to do. That's clear. Now, what about the second one? The second one, you can get two representations in this case, right? You can go into this factor, or you can go into the other factor. So you have two representations. So let me just write it. So now this here gives you pi plus from CL, from spin to n plus 1 to, again, endomorphisms of delta n. So what is this? This is pi plus. So is a composition of this isomorphism projection onto this first factor. So is equal to projection onto first factor. And you get another representation for odd degree spinors, pi minus, from a spin plus 1 to end of. So it's defined in a similar way. So we first see a spin inside this, and then you can project here or there. So you get two representations. So now that's a very interesting situation, right? Because for even spin group, we are getting one representation. For odd spin groups, we are getting two representations. Okay. Now, one of the things that we want to know, question? Yeah. One of the things we want to know is the question of irreducibility of these representations. So that's a bit, maybe next concept you learn after you learn this definition of representation is irreducible representation. So let me, again, that's a very easy concept. Let me recall it for you. So here I can just say, this is another definition. A representation pi is called irreducible if there exists no subspace W inside V, W different from 0, W different from V. So these are called proper subspaces. If there is no proper subspace such that actually pi of G of W is inside W. So in other words, the idea of irreducible representation is, as name suggests, is the following. You cannot just pick some smaller subspace so that you get a representation on that smaller subspace by restricting your operators just to that linear subspace. It can happen. If that happens, you can imagine that that representation, it's not pure. Maybe this can be decomposed into the sum of two representations. So these are not basic, fundamental building blocks of representations. And actually that insight is true. So we are interested in irreducible representations in some sense. And in particular for these two things, we want to know which of these representations are reducible and which are irreducible and what's what. So that's quickly, I'm going to review that stuff. Okay, so that's the idea of irreducible representation. Otherwise, of course, it's called reducible. So otherwise, pi is reducible. Okay. Now, let's look at these representations. So there is a trick here. There's an element that kind of unravels everything for us. So here is what we need. Let omega c be this element, I to the power n plus 1 over 2. So that's the integer part. This is the kind of floor function of this real number, rational number n plus 1 over 2, integer part of n plus 1 over 2. So E1, E2, En, this element belongs to C at n. So you can check the following things. So then one is that, first of all, omega c squared is 1. So this is purely algebraic computation. You can check that if you square this, you get 1. Second, for n equal to odd, n equal to odd, omega c belongs to Z, CLN. So that's the center of algebra. So, so this means that omega cx, it commutes with all elements of the algebra. So it means that omega cx is equal to x omega c for all x belonging to CLN. Okay. And thirdly, for n equal to even, omega c v is equal to minus v omega c for any element v in your vector space v. So if n is even, this element is not central. Actually, on I mean, so it's on odd elements, it acts by, when you switch, you pick up the minus sign. On even elements, though, you get the exact element. If you repeat this twice, like you have VW, then you get minus minus, you get plus. So it commutes with even elements, but it anti-commutes with odd elements. It follows from this. So I mean, proof of this is easy, and it's just pure algebra, and it's very good. So I leave it as an exercise for this week. Yeah. So Luke is taking notes of these exercises. That's good. So this is the first one for this week. Okay. So then we can now use, for example, this part 2 to decompose this space. So for n equal to odd, it follows that we can decompose this CLN as CLN plus direct sum CLN minus. So this is the plus. You see, it has two. This condition implies that it has two eigenvalues, lambda equal to plus minus 1, two eigenvalues, right? And what we can do, we can look at eigenspaces for this 1 and minus 1. So E1 and E minus 1 is eigenspaces, right? So this is the eigenspace 1. And this is eigenspace minus 1. Okay, so this decomposes the whole space into two pieces. Actually, that's exactly even odd thing that we had before. Now, this condition implies that these two things are actually invariant under the spin group. So no, so far I just write this. Okay, so what I want to claim is that so also for n equal to even, we get 3 implies that if n is even implies that omega c x, that's what I was talking about when I was writing omega cx is equal to x omega c for any x belongs to a spin of n, since spin n is generated remember the definition of a spin n. Spin n, we said, is the group generated by products of even number of unit-length vectors inside this Clifford algebra. Remember, spin n was products, the group generated by such things v1, v2, vk, or actually v2k, such that norm of vi is equal to 1 and vi belongs to v. And I said that, well, obviously this is inside this spin group, and this spin is inside CLN, and this CLN inside complex, right? So even because it's anti-commuting with one element, so it commutes with even number of elements. So if you let this spin end act on this space, it actually decomposes, respects this decomposition, and we get this. So what follows? So let me write it here now. Okay, so spin n representation delta n decomposes as delta n plus well, basically, you're acting on this and then you're decomposing the space according to this, and because it commutes with those two components, so it just leaves this environment. These guys have a name, we'll come back to that. This is just some introduction, but we'll come back to it. These are called Weil spinors. So it's called Y. I mean, if you hear about Weil spinors now, you know what's going on. So there are two results that I don't want to prove now, but I mentioned about irreducibility. So first of all, if n is odd, delta n is irreducible. And if n is equal to even, delta n equal to delta n plus dx sum delta n minus gives 2 dx of spin. Okay, so yeah, let's not prove this right now. We will come back to that later on when we will construct all of the spin representation. When we are a little bit more conversant with these things, we'll come back to that. Maybe right now there is no point of discussing this. Okay, so one can say much more about these things, but right now maybe I should just stop discussions about the spinors and ask you if you have any questions.
Could you say a little bit more about the decomposition of the Clifford algebra for n odd? So you said that it was even odd, but I might have misheard. Because I don't think it's even odd.
The Clifford algebra itself?
For for n is odd, we wrote CLN is CLN plus and CLN minus.
Yeah, and I said that actually this decomposition coincides with the decomposition that originally we defined. So let me, you remember, so, right. So you remember that we have this decomposition in general, CLN of VG, right, is equal to CLN VG 0 direct sum CLN BG1. So this was, I mean, this is for any metric, right? And for any V. It doesn't have to be positive, definite, or anything. It could, or non-degenerate. It could be 0, for example. So what is this? This is generated by even number of EIs. This is generated by odd number of EIs. I mean, an element over there, you can always write it as some CI EI, where this index is even number. So I mean, this is, I can just say CI1 I2K, EI1 EI2K, K from 0 up to whatever. And same for this one, right?
Yeah, so what I don't get is how the omega element generates this.
Okay, so this decomposition?
Yeah,
Right, so the omega C, you see we had this isomorphism that so we had the isomorphism that CL n of say, so are we in the odd case? Let's write it in the odd case to be is equal to CL is equal to end of delta n direct sum end of delta n, right?
mm-hmm.
Okay, and then this omega C belongs to this guy, right? So it's acting on this space and on this space. So this decomposition, okay, so, right. Okay, so now this decomposition, so it's where actually omega C is acting by identity, but oh yes, this acts by left multiplication. Okay, right. So omega C acts by left multiplication. On CLN, right? Any element of the algebra acts by left multiplication on the algebra.
Mm-hmm.
Okay, so and then because omega C squared is equal to 1, so you can look at the +1 eigenspace and -1 eigenspace like that. So that decomposition comes from that. And then this fact that I erased here, omega C V equal to -V omega C gives you that this corresponds to the original decomposition that I had.
Wasn't that for n even? Did I get the anti-commuting? Because for n odd, it should commute with any generator.
This was for n even, right? Or was it?
Yeah.
Right. Let me just check with my. Yeah, this is for n odd, right? So we have got this for n odd.
The omega seems to act more like a Hodge star than, like it would induce a similar grading to the Hodge star rather than the even odd.
Yeah, okay, so right now we don't need Hodge star, but yeah, but one thing could be that I think one thing is that there is a confusion now between the spin group and Clifford algebra inside. So there might be something like that. Okay. Right. Yeah, I understand your question. Right. So. Yeah. So why don't I come back to this a little later? Yeah. So. Yeah, no, that's a good question. Right. Okay, so I'll come back to this after the break. Just okay, good. Yeah, so any other questions? Okay, so now we need a little bit of geometry. So I'll come back to this later, of course. So we need a bit of geometry. So let me just tell you what sort of geometry we need. So some basic differential geometry. So all of this actually you can read in chapter 1 of Rho. I mean, you can just, there are many sources, of course, you can just read it in Rho chapter 1. One of the references in both editions you can find. Actually, second edition in this case is better even. Okay, so the idea of manifold, maybe I should not say anything. I just assume that you know manifold, but if you have questions about manifold, let me know. So manifold, I just assume, I mean smooth manifold. I just assume you know, but if you have questions, just ask me. But then the next concept that we need is the idea of vector bundle. So what is a vector bundle over a manifold? So the idea is the following, say a real vector bundle, for example. So the idea is this, we can start with trivial bundles. I mean, so E equal to M cross Rn. So you have to think of this bundle as, so I just write capital N. As geometrically, you think about it like this. This is N, and over each point on N, there is a copy of Rn. Rn. So it's kind of sitting over each copy of Rn, right? And then smooth sections of E so it's denoted by C infinity of E. Well, what is it? So these are like, I mean, so basically these are functions, so functions f or s from M to E such that S of x belongs to EX. Now, if this is X, this is called EX also, and this is called fiber over X, right? Fiber over X. So this is the idea of, we are thinking of fields of vector spaces parameterized by this space M. So it's a family of vector spaces. Parameterized by N. And each member of the family is called fiber over this point. And this is the idea of sections. Now, one thing is that you can just choose Rn, or you can choose a complex vector space. In that case, it's called a complex vector bundle. So you have complex vector bundle. Then in that case, you replace Rn by Cn. And then you go just like that. So in this case, this guy is very simple. In this case, these are just maps S, right? From M to Rn. because all fibers are the same. So, and this is Rn for all x. So you just go to Rn or to Cn, for example. Okay. Now, what you want to do in the next step is you want to make this only locally like that, but globally there may be some twist, like a Mobius band that you have that is locally is like a product if the things are continued forever. So in that case, you have to go out of three-dimensional space, but that's okay. And then you have a situation where only locally you can write this as a product, but globally you cannot write it as a product. So let me just write in general. You can have this picture in mind, a vector bundle. So I just write VB, vector bundle over M is a family. So you know, the locally trivial. So this was the idea of trivial. So now this time you just say locally trivial family of vector spaces parameterized by M. Okay? So what does locally trivialized means is, well, this means the following thing, because we have this manifold, say N. So around this point, there is a neighborhood, open neighborhood U, such that over U, your E is equal to not M cross Rn, but U cross Rn. So locally, you can always do that. And these local trivializations have to be compatible in a certain sense, which really right now doesn't matter for us. But this local triviality, I can just say the following. So there exists this framing. So now I introduced the idea of framings. There exists local framing. So what is local framing? The local framings are these functions E1, E2, En from U to, for example, E restricted to U. So over this, right, we have got these fibers, Ex, and we have these functions from U to E restricted to U. These are smooth sections. Such that at each point they form a basis for that fiber over E, right? Basis for fiber over E. Over U, sorry. I mean, for fibers over U. Okay, so this is called the local frame. So it's like a frame of reference or basis for things, but this is called local frame. Now, examples. Of vector bundles over manifold M. What is the most basic vector bundle you can imagine over a manifold M?
The tangent bundle.
Exactly. Absolutely. Thank you. E equal to Tm, the tangent bundle. Of M. what is this tangent bundle? Well, I mean, in this case, at each point, there exists a vector space which is the tangent space. Okay, so then it changes from point to point. So this is the tangent bundle of them. Now, the tangent bundle to a manifold could be trivial or very well could be non-trivial. So e.g. for n equal to S2, Tm is not trivial. So can you give me the reason why this bundle is not trivial?
If it were trivial, would it have no curvature?
That's true, but alternatively, you could say, because that uses the idea of curvature and all these things, but maybe we don't want to use it right now. It will come soon. But you can say, what would be local triviality implies? Proof. What triviality would imply? Any trivial bundle, by definition, has a global framing like this, right? Has a global framing. I mean, because it's, you know, I mean, if Tm, say, if E is equal to n cross Rn, then you can just choose E1x to be E1. I mean, the basic vector E1 here and E2x to be E2, Enx to be En, the standard basis of Rn, right? So you would have a global framing, and in particular, there would be a vector or section that is nowhere zero. But then there is a theorem, a Hale-Ball theorem, implies that there exists nowhere zero vector field on S2. Actually, this is not the implies, it is exactly this statement that on S2, right? It's not possible to define a vector field which is continuous. Of course, in this case, we are even asking for a smooth, but continuous is not. It changes in a continuous way and is never zero. Right? So this is the content of Hale-Ball theorem. So this Hale-Ball theorem, which is a classic result of first course in algebraic topology, undergraduate or first year graduate thing, would immediately imply for you that this tangent bundle of S2 is not trivial. Now, a nice exercise is the following. I want you to show that actually tangent bundle of S3 is trivial. So that's a nice exercise. Trivial. Its tangent bundle of S3 is trivial. And the question is, for what other n, and also, of course, tangent bundle of S1 is also trivial. This is even easier. This is interesting. But now the question is, for which n can you find another n such that tangent bundle of Sn is trivial. So this is something you want to look into that. So it's a nice question in this case. Okay, so now, so about tangent bundles, I think we have these great examples that we can work with, and we have this idea of framing. So I can just take a 10 minutes break till 3:05, and then we come back. Okay. Okay, so now let us close this. Okay, so just a bit more about vector bundles. So this is called operations on vector bundles. So, so let us recall from linear algebra. We have these operations on vector spaces, right? So, for example, if V is a vector space, then you can construct V star, which is called the dual of V. This is hom of V and R over R. So this is called the linear dual of V, and this is another vector space. It's called the dual space of this linear. Right? So, for example, if dimension of V is less than infinity, implies that dimension of V star is equal to dimension of V. And in fact, in this case, you can do something nice. If you choose a basis here, basis of V, you can construct a basis E1 star, E2 star, En star, basis for V star that has the property that Ei star on Ej is equal to delta Ij. Okay? And in fact, it's better to put these things up here. So Ei star. So this is one operation. And then we have like Direct sum operation. And we have also tensor product operation. Tensor products over R of two vector spaces. You can also do tensor product many times, like V tensor 2, V tensor 3, V tensor 4. And you can also do tensor product of mixed, like V tensor 2, tensor, say, the V star, tensor 3, etc. So these are basically ways of constructing new vector spaces out of old vector spaces by these operations. Basically, you have duality, you have direct sum, and you have tensor product operations. More or less these three operations, and you can construct a lot of new things out of these things, right? Now, the point is that we can actually take these things and do all of them for vector bundles as well. So that's a good thing. So big idea is that all these concepts, operations, have analogs in a vector bundle theory. So for example, this one prime, for example, if you have a vector bundle E, so my notation for vector bundle is this, then you can construct a dual bundle by this. So basically, I mean, the rough idea is that, I mean, there is a precise definition you can read, but the idea is that fiber-wise, if this is E, fiber-wise, then you do, so this is like EX. When you construct E star, it turns out that each fiber is actually the dual of the corresponding fiber. This is, of course, the idea. This is not the definition. And there is a definition, you can, as I said, but it's better to get the idea first, and then you can read the definition. And second, you can just direct sum of bundle. So direct sum of vector bundles. And you can also take tensor products of bundles, vector bundles. This is tensor products. So a lot of these constructions in linear algebra can be transplanted to the kind of vector bundles. So basically, what is vector bundle theory? Vector bundle theory is parameterized linear algebra, if you want. It's a family version of the linear algebra. So let me write it here, because this is a good sentence. Vector bundle theory is parameterized linear algebra. Okay, so these things, because we are always going to do a lot of local calculations, and then in this case, if you have a frame here, for example, E1, En, local frame, you can dualize these things by that method. So this is the dual frame. So this is quite useful to have this. Okay, so we'll, yeah, we take these ideas later on, actually soon, so that's, okay. Any questions now? Or? Okay, so let us now start differential geometry of these bundles. So the main idea that we are going to use in this course is the idea of connection. So this is connection on vector bundle. So let us fix smooth vector bundle. So my notation is always like this. Sometimes we also write E over M. I mean, smooth vector bundle. So this definition now is important. A connection on E is a linear map so this is a linear map nabla from C infinity of Tn cross C infinity of E to C infinity of E. So notation is that sending a pair X and a section S to nabla S x, such that, first of all, in this variable x is linear. All f belonging to C infinity of n. And second condition is this Leibniz rule. But if you multiply this and take covariant derivative with respect to x, or take a connection with respect to x, that's equal to f nabla s x plus x over f times s. So let me explain these things, because this is something that has to be defined, but that's okay. First of all, as I defined, this was our first example of vector bundle. This was the tangent bundle. So C infinity of Tn is smooth sections of Tm. So of course, smooth sections of the tangent bundle is just vector fields on the manifold, right? So that's equal to space of vector fields. That's this one. I mean, of course, the infinity of m is the set of all maps from x to f from x to r, to r, or to c. I mean, some people take it to c, some people take it to r. It doesn't matter. In this case, we just take it to r. That's fine. So this is just, let me be specific. It goes into r. So what does these two conditions mean? The first condition means that it's linear with respect to this. Of course, now you see, f s. So what is this? Well, f s of x is just f of x, s of x. So that's just pointwise multiplication, right? Okay, so that's this one. Now, there is something that it's very important to notice. The first condition, this condition implies that. Any questions about this? At least the semantics of this? I mean syntax, not semantics. The syntax of the definition.
For the first condition, why is f in the smooth sections on M and not Tm?
Oh, you see, fx is a smooth section of Tm, right?
Mm-hmm.
Because we can multiply. X is a smooth section of Tm. So what we want to know is that what happens if you have a vector field and you scalar multiply it by some function, but this function now could change from point to point. I don't want to say it's just for f constant. I want to say for all functions. And by the way, I should say this map is R bilinear. I mean, because this is an R vector space, this is an R vector space, so this map is R bilinear. So that's I should, yeah. So, but this is a condition that I will put, and now I want to tell you what kind of thing it implies. So that's a very, very strong condition. But your suggestion, f to be smooth sections, then if I have a smooth section of Tm, I cannot multiply by another smooth section of Tm, right?
Right. Okay, that makes sense.
So multiplication of two vector fields is not defined.
Mm-hmm.
So, but this condition puts a very strong restriction on the nature of this nabla, by the way. Yeah, so that's. Okay, yeah, this was a good question. Thanks. Yeah. So, any other questions about the just formality of the definition, at least, before getting into this is one of the most important definitions in this whole course, by the way. So. Okay, now let us get to business about this. First of all, one implies that the value of this, because this is a section, right? The value of this guy at P only depends on x at P. So in other words, the value of x at P, not x at other points. So this is quite interesting, right? Because we are saying that originally I told you that I have an operator that takes a section and so differentiated along this. By the way, I mean this idea of, so let me just write, idea of this notation, nabla Sx, is basically derivative of x. I mean, it's basically directional derivative of S along vector field X. So this is notion of derivative, taking derivative, but directional derivatives, as in calculus. In calculus also we took directional derivatives, right? We have this operation dfx that was like gradient of f dot x, right? Remember from calculus? And this is the generalization of this calculus idea. Okay, so this is what is going on here. So this is the directional derivative or derivative, but it's also called covariant derivative. So another notation is covariant derivative. So this is good to know. So this is covariant derivative. So this is one thing. So you understand what it's saying, right? It means that if you have two vector fields, x1 and x2, that only match at P, then the values of this covariant derivative of S at P only, then they match. At P they match, right? So let me just tell you the exact meaning of this then. I.e., if x1 at P is equal to x2 at P, then nabla S x1 at P is equal to nabla S x2 at P. Yes. This is what, so this is an exercise. You have to go through mechanism of proving this. So let me give you a hint. Yeah, so the hint is that, yeah, really, my only hint is to use one. I cannot say more. So let me just not say more about this, because if I say anything, it will just kill the joy. So, okay, so now what about 2? Let me just draw some conclusion from 2. So this is, I explained here. So let's go to 2. 2 implies that the difference nabla 1 minus nabla 2 of fx s is equal to f nabla 1 minus nabla 2 of s at x. So you see the notation, right? So i.e., the difference of two connections is C infinity of M module map or linear in X variable. Okay, so this map now is very interesting. This observation is very interesting. I mean, this is very easy because you subtract and you notice that this offending part cancels. By the way, nobody asked me about this. Do you know this notation? Nobody asked about this. So let me explain that, and then I will tell you what does this mean. This is exactly the idea of directional derivative that I mentioned. So this is directional derivative. I mean, this is like sum df dxi xi in local coordinates. So this is the idea of this is gradient of f times x, or basically df in the modern notation. This is df acting over df is equal to differential of f. So in local coordinates, you can define it like that. In this case, this is the one. All right. So what else I want to say? So this property 2 prime that I just erased implies that. Okay. So for any nabla and for any a, nabla plus a is again a connection. So what is a? Well, a is the following thing. A from C infinity of Tm plus C infinity of E, C infinity of E is R bilinear and satisfies F S X equal to F S X, A S F X is equal to F A S X. So such a thing, we can think of it as going to from A, from C infinity of Tm to, okay, so let me not write it down because that's just too much notation at the same time is not a good idea. So any questions or? Okay, so, right. So now, so the question now is, examples of such things. What if your bundle is trivial, for example? The trivial bundle. Then by these observations that we have, then any connection is of this form. Is of the form. So basically this nabla of S x is equal to sum d s dxi, right, plus as. So let me write this, explain this, where a goes from m to mn of r is a matrix valued map and this is just we are just differentiating and putting it in this so because this is a vector, right, and we are just differentiating, so we are producing a column of vectors. So that's so why is that so? I mean, the idea, so proof of this is easy. If you subtract nabla from this ddxi operation, so this let's call this nabla 0, for example. If you subtract nabla from nabla 0, then you get a, and by this observation, a is such a map. You can check that really, C infinity of this, you're just really going from oh, okay, so here I need to go from C infinity of Tn, sorry. Okay. So I should put AI maybe here. Yeah, I should, okay, better notation is just to put AI. And then here I put AI. So yes, matrix valued maps. So I equal to 1. So what is S? Let's try to understand this formula, because this is a kind of the essence of thing is really this formula. You see, S is going from M to Rn, right? So we are thinking of this. Okay, so this is, I should say, EI, sorry. Okay, so I have to introduce some notation now. Okay, right, this is the right notation. Okay, so in this section, yes. Now, another notation which I could have introduced before is the following. If you have a coordinate chart, yeah, for any coordinate chart, on U inside M, so this is a coordinate chart. Then there is a basis ddxi, which we denote by di, I suppose, yes. Basis for Tm. And as I said, so we can see this as a framing of Tm, right? Locally restricted to U. And the dual basis is dxi. Okay. Dual basis. Or star of them. I'm not using this, but I will use this soon. So, but this is the basis that I'm using here. So I'm saying that in order to take covariant derivative of S with respect to these frames, at least these frames, SIs, you use this formula. And then I have to tell you how to extend this to general. But I mean, to extend this definition in general, you just write x equal to sum, say, fi di, right, according to this first basis frame result. And then you define nabla x, nabla s x is nabla s sum fi di, and we just use the property 2. So this is equal to sum of nabla s, I mean, this is just additivity right now. And then this is equal to fi, so sorry, sum fi nabla s di plus fi acting on di, and then s. This is just the second property of the connection. So once you know this, the value of the connection with respect to some frames, then you know it for everything, because you can just use property 2 to write down what is the value of your connection on arbitrary vector fields, covariant derivative with respect to arbitrary vector. So this comes. So that's any questions? I highly recommend you go through chapter 1 of Rowe's book, which is in resources, but and also in the review tutorial, go through this concept. That's important. Okay, so now let me. You see, all these ideas are very algebraic ideas. I mean, you can do these things in great generality as algebraic ideas, but I don't want to go into the algebra too much. Okay. So now, finally, the curvature of a connection. So now, so let nabla be a connection on the vector bundle E. The curvature of nabla is the operator nabla. Oh no, K, sorry. From C infinity of Tn cross C infinity of E, actually C infinity of Tn cross C infinity of E cross C infinity of E. Defined by K of, so X. So I should use notation Y, and then so S1 or S. so to speak. It just has three variables. This is equal to nabla x, nabla y, s minus nabla y, nabla x, s minus nabla xy. So this is a fundamental curvature operator. So let us unpack. You see, x and y are smooth vector fields. Smooth vector fields. And S is a smooth section. So you see, this is a very complicated operation, as you can see here. So let me try to explain at least part of it, because it takes a long time to fully grasp some aspects of it, not all of it, some aspects of it. So let me, first of all, we have this operation nabla Sx, right? I said that this is the derivative or the rate of change of the vector field, of the section, if you move along this vector field x. But this is like the second rate of change, right? So because we are differentiating along this vector field, say, x first, right? Or y in this case first, and then we differentiate along another vector field, y. Okay? So this is one vector field, these are flow lines of this vector field, and this is flow lines of the other vector field. So we are differentiating along different vector fields at the same time. So this is the second degree derivative, essentially. So this is second derivative. Second derivative. Covariant derivative is first derivative, as we saw in the example, but this is second derivative. Now, what is this? This is the bracket of two vector fields, right? Okay, so now something really amazing. Any questions about the notation at least? Yeah, it's a complicated operation. It takes one vector field, actually two vector fields, and one smooth sections, and spits out another smooth sections, which is essentially the second derivative of your smooth section in two different directions. I mean, second derivative in higher dimensional space, you have different mixed directions, right? So this is kind of very, very abstract version of mixed partial derivatives of vector fields, basically. But there's a lot more. I mean, it's not just because this is also mixed partial derivatives, but we are subtracting from this, and we are still subtracting from that. So there is a lot of subtleties that are hidden in this formula. Now, one thing that is very, very important is the following lemma. The lemma is that this K is a infinity of M linear in all three variables x, y, z. I mean, in x, y, s, i.e., nabla, so K of fx, y, s is equal to K of x, fy, s equal to K of x, y, fs. That's equal to f times K of x, y, s for any f belonging to C infinity of n. Okay. So if you think about this, this is really amazing, right? Because you see, I said that we have no right to assume that actually it is not, that nabla with respect to this down variable is linear, because it comes like f nabla x plus some correction term. Right? And this is again, same here, and of course same here. I mean, this is so complicated. And with respect to s, again, the thing gets, with respect to s, maybe is not difficult. No, yeah, with respect to s is okay. Only with respect to x and y is surprising. Yeah. So this is quite surprising, and it's just a pure computation. You have to compute it. So that's why I leave it as an exercise. So you should do this exercise to learn some of the properties of this thing. So this means that actually the curvature operator, so let me now write it. The consequence of this lemma is the following. Corollary. The value for any p belonging to M, the value of, k, sorry, of x, y, s at p, the value of k at p only depends on x at p, y at p, s at p, and not on neighboring values. Not on neighboring values. So this is quite remarkable, right? Because, I mean, when you differentiate a function, for example, the value of the derivative is not that just depends on the value of function at that point. That's totally wrong. It also depends on the value of function on the neighborhood of that point, right? And for second derivative also, I mean, second derivative also depends on the value of the function on the neighborhood of that point. But somehow, magically, this construction is such that it's actually independent. If you give me the value of x, y, and s, although we are differentiating, and we are differentiating twice, but this particular mixture is oblivious to the value of x, y, s at neighboring points. So this is quite remarkable, and I want you to think about it. Just so this is just x at p, y at p, and then s at p. So it basically tells us what is the amount of variation of s with respect to these two, mixed variation in these two directions is independent of neighboring values of x and y. It's just an RS. It just depends on this point p. It's really amazing, and this is just a formal consequence of this. If you do the two problems, two kind of exercises before, you will be able to do this as well. So this is similar to. Okay, no, let me not write. Okay, now one more thing I should say. So there is a special case. connections on vector bundles. Oh, yeah, on tangent bundle, yeah. Vector bundle, that's what we did on tangent bundle. So let's assume E is equal to Tn, right? Tangent bundle. Then this whole theory that we developed gives us, of course, the notion of connection on tangent bundle, but it becomes much more symmetric and it has some extra features. So this nabla is C infinity of Tn plus C infinity of Tn goes to C infinity of Tn, right? You see, this is E now. So this is nabla yx, right? So yx, pair yx is sending to that, right? And curvature also, k, we just write k x y z. I mean, everything here is just on the same footing because they're all now vector fields. Before there was just two of them was a vector field. This one was a smooth section, but now this is also a vector field, which is a smooth section of the bundle Tn. Okay, now what I want to say in this case is that there is now the last theorem or last thing we need to do in this case is compatibility with the metric and the Vicilito connection. But this we can do on Wednesday actually, because I mean there is enough. So I think we are good now. Okay, so I just pause.